In the name of the Almighty, the Compassionate, the Merciful. Now we come to our next in this lesson, we come to our second part of our series of lectures, which concerns the theory of integration. As you remember, in our last lesson, we said that integration was discovered prior to differentiation. In fact, these were tedious methods for obtaining, for calculating areas. But it was thanks to Newton, in fact, and Leibniz, which discovered the fundamental theorem by which one can use antiderivative or what Newton called the inverse tangent in order to calculate definite integrals. In other words, one has to study ways for calculating antiderivatives. And of course, prior to this, one has to know the theory of differentiation. So in fact, it means that we have to teach differentiation, then calculate antiderivatives, and then integration. The only drawback with the fundamental theorem of Newton and Leibniz is that it considers only continuous functions. In fact, Cauchy made progress when he succeeded in proving that the function might not be continuous, and yet it has antiderivative, because continuity is a sufficient condition for a function to have an antiderivative, but it's not necessary. A function might not be continuous and has an antiderivative. And then later on, and this is why his fundamental theorem is much more flexible. And then came the role of Riemann when he succeeded in proving that a function may not be both neither continuous nor having an antiderivative, and yet it can be integrable, in which he called his functions integrable functions. And then we are back to square one, because actually what Riemann did is that he defined what a sum called Riemann sum, by which if the limit exists, then the function is integrable. And in fact, this is exactly what Archimedes and Alhazen did. The only exception, the only difference between both is between either of the two and Riemann is that their functions were all continuous. And why? Because actually they didn't consider continuity and discontinuity. This was in fact something it goes without saying. These people were not incapable of studying continuity. In fact, they were not only mathematicians, they were mathematicians, engineers, philosophers, and physicists, etc., all of them. And they could have studied continuity, of course, but they were not interested, because all phenomena, they were practical people. All phenomena which they studied were practical phenomena. And then if we consider now integration, the meaning of integration, in fact, integration means accumulation of areas. And this is why in books we find there are two directions, two approaches for teaching integrals. Either we start by, like in books of analysis, by the integral, and we say this is the limit of Riemann sum. And then we consider antiderivatives as special case when the function is continuous. Or we do, what we are going to do is that we start by antiderivatives, and then we mention Riemann at the end for integrable functions as a generalized form of our integration. This, in fact, is the best thing, because students, in fact, what they do in their study in engineering, all they do is to calculate antiderivatives and use the fundamental theorem. And in fact, whether antiderivative is an integral was a question that was brought about during the evolution of calculus, because people reject the idea that antiderivatives are integrals. In fact, they are. And the question actually was brought up during the evolution of this science, as I said, whether integration is the area below graphs of functions, like it was adopted by Newton and Leibniz, or whether integrals, whether integration is the anti-process or the anti-differentiation, the converse of differentiation, and that was adopted by Bernoulli, Bolzano, Lagrange, and Euler. So whether really antiderivative or integration is the converse of differentiation, that was actually the two questions that were solved. This question actually was resolved finally by Cauchy when he discovered his fundamental theorem, because in fact Cauchy said the following, that the integral from a to x of a function having an antiderivative f of x or f of t dt is equal to capital F of x minus capital F of x minus f of a, where f prime is equal to f. Now, if we differentiate this with respect to x, you get here f of x. So it just means that this part here is at the same time it's an antiderivative of a small f, because when you differentiate you get f, and the same way it's a kind of integral. In fact, it's a definite integral even, not only indefinite. Of course, it's indefinite in the sense that here your arbitrary constant and here is x, and it gives you the area under the graph f of t dt for all functions which are continuous, but at the same time it's an antiderivative. And this is in fact the same thing which Newton did. Newton, what he did is that he took any graph like this, and he start from A, and this is x, and this is x plus h, and this is the area. He considered the area at x plus h, which is all this area here, A at x plus h, and he subtracted the area at x to obtain this piece of area here, this piece here, and and we know very well that this piece of area here is almost a rectangle of base h and of height f of x, so he gets almost f of x when h is small. So if you divide this by h, you end up with what? You end up with f of x. Indeed, what is that? This is, in fact, he didn't choose a limit at that time. But in fact, if you take the limit when h tends to 0, this is exactly dA by dx. So what Newton, in fact, has obtained is what? He obtained the following, that A, the area, is the integral of f of x dx, which he called inverse tangent. And not only that, but since dA by dx is equal to f of x, so in fact A is the antiderivative of f. So actually we can consider antiderivatives to represent areas, but areas that are not definite, indefinite areas. And this is why we call indefinite integrals. And in these indefinite integrals, actually there are family of functions that are not indefinite, contrary to definite integrals, which represent a precise number, which give a precise number. In this lecture, in fact, we are going to speak about the notion of the indefinite integral, and then the remarks, we should say some remarks on the antiderivative, and then we are also going to speak about antiderivative of some functions and their properties, etc. First of all, we talk about the notion of the indefinite integral. An indefinite integral, when we say antiderivative, it means try to find for a function small f, we wish to calculate the antiderivative of this small function f. So we say a capital F is an antiderivative of f in interval I if f prime, capital F prime of x is equal to f of x. If you can find a capital F of x such that its derivative gives a small f, then we say that capital F is an antiderivative of small f. So actually this is simple then. Suppose, for example, we wish to calculate the antiderivative of f of x is equal to x cubed. Now, what is the function when we differentiate it? We get x cubed. It's simply a quarter of x to the power 4, because when you differentiate quarter to the power 4, you get x cubed. Of course, this is very simple. The function is that. This is an antiderivative, as I said, because you differentiate, you get x cubed. But you might as well also consider something like this, quarter of x power 4 minus 15. And you also end up with x cubed. So in fact, quarter of x to the power 4 minus 15 is an antiderivative as well. And this is why when you ask students to calculate the antiderivative, we don't say calculate the antiderivative of f, but we say it instead calculate an antiderivative of f, because there may be more than one antiderivative. For example, again, calculate an antiderivative of 1 over x. You may get ln mod x. Why? Because the antiderivative of ln mod x is equal to 1 over x. Actually, here we should state some remark here. Suppose you wish to integrate 1 over x dx. You may wish to put it this way, and this is correct. There is no need to put the modulus. This is when you consider antiderivative. But suppose you wish to calculate, for example, the area under the graph of 1 over x, which goes on the left and right hand side of the origin, and you wish to calculate the area, for example, from minus 2 till minus 1. So the area becomes what? Becomes the integral from minus 2 to minus 1. And here you have to substitute, for example, minus 2 to minus 1. But there is no such logarithm of minus 1 and minus 2. Because the logarithm function exists only to the left of, to the right, I'm sorry, in other words, for x greater than 0 only, for positive values of x. So what you do, you should put here modulus of ln x. And you end up with what? You end up with ln 1 minus ln 2, which this is 0 and this is minus ln 2. And why is minus ln 2? Because minus ln 2, in fact, is negative because the area here is below the x-axis. What remains here is to prove whether ln mod x had the same derivative as 1 over x like ln x. Yes, indeed, this is true. D by dx ln mod x, you use the chain rule. You set this equal to u, so you derive d by du of ln u times du by dx. So in fact, you get what? You get 1 over u, which is mod x, times the derivative of mod x. We deduced it before, which is mod x over x, and you end up, in fact, that the derivative of ln mod x is the same as the derivative of x, as expression is equal to 1 over x. So in fact, 1 over x, you either put it ln x if you are talking about any antiderivative, or you might be more precise, because in fact, why are we interested of calculating antiderivatives? Because we are going finally to use them in the fundamental theorem. We are not just calculating antiderivative for fun. No, we are using antiderivative in order to insert it into the fundamental theorem. So in fact, we should be more precise and put instead of ln x, ln mod x. There are actually some remarks about antiderivative. It looks as if it is very simple. All you have to do in order to calculate antiderivative, given a function small f of x, try to calculate a capital F of x such that its derivative is equal to small f of x. And you search in literature, in books, for example, you keep searching for in the derivatives, in the chapter of derivatives, for those functions when you differentiate it, you get your derivative, which is given. But in fact, this concept is not that simple. Why? Because first of all, not every function has an antiderivative. For example, this function here, which is the sine function, which has a positive, which is equal to 1 on the right-hand side and minus 1 and equal to 0 at the origin. This function x, as a matter of fact, has no antiderivative. Why? Because it does not satisfy or verify a theorem called Darboux theorem for antiderivative, and therefore we're not going to go through it. But in fact, this function has no antiderivative. So in fact, not every function has an antiderivative. Again, not every elementary function has an antiderivative in the form of elementary function. For example, cosine x square. Some of your colleagues might tell you that we cannot integrate cosine x square, find an antiderivative of cosine x square. Or for example, the integral of x square dx. No, in fact we can, because these functions are continuous. They're composite function of continuous function, and therefore they have antiderivatives. By theorem, from the first fundamental theorem. But the problem is that there is no such elementary function which can, the one that we know of, the elementary function that we know of, that can represent these antiderivatives. Again, finding an antiderivative is not an easy task. It's exactly like, for example, somebody wishes to teach you how to drive a car. First of all, he teaches you how to get to the first gear, second gear, until the fifth gear, and then he leaves the rear gear at the end. Why? Because usually the converse process of any elementary process is more difficult. For example, subtraction is more difficult than addition, and usually we teach the student, our children, to add and then subtract, or to multiply then to divide, and same thing. We teach them differentiation, then integration. So because integration is the opposite, the contrast or the opposite operation of differentiation, so it's more difficult. And this is why from first sight we cannot actually calculate the antiderivative of these functions just by sight like this, though they exist all in form of elementary functions. Similarly, expressions, when you have expression of this sort, f of x and g of x resemble each other. And actually, the derivative also resemble each other. They are simple to obtain, yet the integrals are not the same. Antiderivatives look very much different from one another. For example, while the antiderivative, for example, of f is 10 minus 1x, that of j is so intricate like this, so complicated like this. So in fact, integrals, they are not easy to obtain. And this is why, in fact, we encounter books that are specialized in integration. They tell you the antiderivative of functions. There are big books like this. Of course, they are not interested of giving their names to students, because we are not concerned with all antiderivatives, just elementary of some of the functions of which you are concerned with. Again, this is one important property. The antiderivative of a function may not be unique. And this is something unique about antiderivatives. You don't say find the antiderivative. We say find an antiderivative. For example, all these functions are antiderivative of x cubed. X cubed, if you differentiate a quarter of x to the power 4 or 1 over 4 x power 4 plus 3 or 1 over 4 x power 4 minus 15, all of them gives x cubed. And therefore, we call these all antiderivative of the same functions. And not only that, even if you have a function like this, for example, a function plus 1 and minus 1, this we know this is the derivative of what? Of mod x. So we can consider mod x to be an antiderivative of this function. But this is not the only one. It may also be like this. Like this. It might be like this. It may be, for example, x plus c1 and minus x plus c2. This is again another antiderivative. So in fact, antiderivatives are not unique. You may have more than antiderivative. And the integral, what the meaning of an indefinite integral? The indefinite integral is the antiderivative plus a constant c. And this c, in fact, is what we call an arbitrary constant. And this is why, and this arbitrary constant is very important. So in fact, if you have two functions, capital F and capital J, which are antiderivative of a small function f over I, then you must be sure that they both differ from by a constant. And this is one point that we should remark. Suppose, for example, you have an integral of sine x cosine x dx. And you wish to integrate this. You have actually two options. Either you say that this is the integral of half sine 2x, because sine 2x is equal to twice sine x cosine x, or you may do it by simple substitution. You know very well that this integral is equal, which is sine x again cosine x. This is the derivative of this. So you may end up here. You end up with what? With quarter cosine 2x, of course negative, and this one is what? Half sine square x. So in fact, now you have two different answers. Which one is the correct one? In fact, neither of the two. This is special one and this is special one. But if you add up here c1 and you add up here c2, then you may find a relationship between the two, because if you substitute cosine 2x is equal to 1 minus twice sine square x plus c1, then you end up with this form here. Here you get what? You get minus 4 plus 1 over half sine square x plus c1. So you may say that your c1 minus 4 is equal to c2. You may say that. In fact, not only that, you may add another constant as well. So in fact, when you calculate antiderivatives, you may not end up with one result. But what you do, there might be a kind of similarity. Why? Because you always forget about your c1 and c2. These are important things. Otherwise, you get things which are nonsense. And exactly like, for example, this is as a practical application. For example, if you throw a body up vertically upward with the velocity 10 meters per second, for example, and you wish to calculate the distance at any time. So you say that you are subject to the gravitation, the second law of Newton, and this is what it tells you, that the second derivative of s, which is distance with respect to time, is equal to minus g. So the antiderivative of this, which is velocity, is equal to what? Minus gt plus here plus c. So if this g is equal to 9.8, and you, for example, you start with 10 meters per second, so when t is equal to 0, your velocity must be 10, so you end up like a relation of this sort, t plus 10. This tells you what? It tells you that the velocity it depends on your 10 here. In fact, if you put c, then you end up with different velocity. All of these are valid. The only difference is that they're different with 10. In other words, you got the same law, but they differ in what? They differ in the velocity in which you throw your body with. You throw in your body vertically with 10. You may throw it with 10 with 100 meters per second. So each time you use another velocity, you may get another curve, which is again the antiderivative of the same function which you started with, which is minus 9.8. And if you integrate it twice, you get minus 4.9 t square plus 10t plus again another constant c. When it depends, have you thrown it from the surface of the ground where c is equal to 0 at t equals 0, or from, for example, the top of a cliff, for example, which is higher by 100 meters. So you put here 100. And this is what? This is equation of a set of parabolas that it may look like this. All of them are valid. This is S and this is V. So in fact, when you speak about antiderivative, you are not speaking about one antiderivative. You are speaking about family of antiderivatives, and we call them the integral. So in fact, the integral which you speak about when you say indefinite integral, you mean a family of antiderivatives. The only thing which is important about it is that you recognize before that when we say f, you say that f maps x into f of x, and this is unique. You said functions must comply with certain rules. For each x, there must be one f of x. And same thing with the derivative, because you're using limit, and limits gives you unique values. 1x into df by dx. Whereas if you speak about integral, then it maps x into the integral of f of x dx. So here, this is a kind of antiderivative, I'm sorry, an indefinite integral, and this indefinite integral is represented by a series of antiderivatives plus a constant c. In other words, you end up with a family of these antiderivatives. For example, you have, suppose you wish to calculate the antiderivative of cosine 2x. So cosine 2x, what is the function which has as derivative cosine 2x? Is equal to half sine 2x plus c. And this c means what? Means that for each c there is a curve. And this curve represents what? The value of f, which is capital F, and this capital F is the antiderivative plus c. In other words, you get a family of antiderivative, and this family of antiderivatives is what you mean by the indefinite integral of a function. And for special c, if you put c is equal to a certain value, it means that you're choosing one antiderivative, and this one antiderivative pertains to your problem, whether you are throwing a body or whether you're watching a chemical reaction, etc. Suppose now we speak about elementary functions. You have here, these are known. These are the antiderivative of small f. If you have xn, we know very well that the antiderivative, and in these formulas of integral, of course, we have to add up c, because we said you have. This is important. This is important that you wish to calculate the indefinite integral. In other words, there are no one single antiderivative, but there are a series of them, and therefore you have to add up the c. So the integral of x to the n is equal to x to n plus 1 divided by n plus 1, because the derivative of this is n plus 1 x to the n, so it cancels out n plus 1 to obtain xn. And these actually are known. The integral of e to the x is e to the x. The integral of 1 over x, we said, is equal to ln mod x plus c, and x is not equal to 0 because 1 over x exists on the left and right hand side of the origin, and therefore x is not equal to 0. And the integral of sine is minus cosine, the integral of sine is sine, etc. The integral of the tan is ln mod x. These are elementary functions that you should not memorize, but at least know them. All the elementary functions that we have passed by in our course of differentiation, you must also know them offhand. Now we come to some properties of antiderivatives. First of all, this looks very like the Cauchy formula. The integral of f of t, you could have very well used the integral of f of t dt, and you differentiate with respect to x from a to x, and you get the same function here. This is satisfied when small f has an antiderivative. Of course, if it is continuous, then it goes without saying, according to the first fundamental theorem, which we shall speak about. Again, when you differentiate under the integral size, as if you are differentiating then integrating, or integrating then differentiating. So the second property here tells you this. It tells you that the differentiation of f of x, when you integrate it again, you get what? You get f of x, and this is simple. But you have to add up c because you are integrating, and therefore you have to add up constant c. For instance, here, for example, for your indefinite integral, sometimes they leave it like this, and sometimes they put from a to x of cosine square root of t squared plus 1 dt. Same thing. When you differentiate an integral, you get the f of x. And this is one thing. So actually, these are two together, along with the other properties that we evolved. We said that if you have two antiderivatives of the same function, then they must differ by a constant. Again, here the derivative of the integral is equal to the function, and the integral of the derivative is also equal to the same function plus a constant. We move again to properties of the indefinite integral. If you have two functions f and g, and these two functions are have an antiderivative in I, if you integrate, suppose you know the antiderivative of a function small f of x, and you multiply it by c, you forget about c, and you put it outside the integral. In other words, the integral of 5 f of x is equal to 5 the integral of x, and this goes without saying. These are simple forms which you use always. When you have constants, you forget about them and you leave them outside the integral. Again, the integral of the sum of two functions is equal to the sum of their integrals, indefinite integrals, and this is known. When you integrate, for example, suppose for example you wish to integrate, for example, y square plus cosine y dy. What you do is that you separate this. Integral of y square plus the integral of cosine y dy. So the first one gives you what? 1 cubic y cube, while the second one gives you sine y. Of course, you don't forget about your constant c. This is how it is done. And of course, if there is a negative here, you put negative as well. Evaluate the square root of t minus x squared t plus 1 dt. This is exactly what we have just talked about. You separate. This is equal to the integral of the square root of t minus the integral of x squared t plus the integral of 1. The integral of square root of t is equal to 2 over 3 t to the power 3 over 2 y, because the derivative of this expression here is equal to square root of t, while the derivative of the integral of sec squared t is equal to tan. Why? Because the derivative of tan is equal to sec squared. Again, what is the derivative of the what expression, what function has as derivative 1 the constant? It's a linear function of t. T has derivative 1, and 0 has a derivative, has an integral constant. So in fact here you put t and then don't forget the constants. If you wish to evaluate the integral of y plus y square, here it's simple. What you do, you expand this. This is a binomial, and when you expand it, you get what? You integral of sum of functions. So you apply the same rule, the sum of the integrals of function. So you get 1/3 y cubed minus 1 over y plus 2y. This is the integral of y square. This one is the integral of 1 over y square, because here y to the power minus 2. So you apply y to the minus 2 plus 1 divided by minus 2 plus 1. This is simple. And again, 2y dy, 2y plus constants. Evaluate the integral of 1 cosec x cotan. This looks a little bit complicated, but it doesn't matter. When you see trigonometric functions, you wish to transform into sine and cosine, because sine and cosine are very simple. The derivative of sine is cosine, and cosine minus sine. So in fact, I don't like to see expression of this sort, so I transform it into sine square over cosine. Directly when you see sine square over cosine, they look apparently there must be a kind of relation between the two. Why not, for example, substitute sine square by 1 minus cosine square? And these kind of tools which you use all the time, which are relation between trigonometric functions. So if you do this, you separate, in fact, your function into all functions of cosine, which you know the integral. So if you substitute sine square is equal to 1 minus cosine square divided by cosine, you end up with sec minus cosine. Now the sec is an elementary function of which the integral is different. Indifferent integral is known. The integral of sec is ln sec plus tan, and the integral of cosec is ln cosec minus cotan. These you have to look up in any text, and one should know the basic rules of the indefinite integrals of elementary functions. And as to the second one is simple. The integral of the minus cosine is minus sine plus c. Prove that f double dash of x is equal to f prime of x. It's simple. This is one application of the properties of the antiderivative. All you have to do is you can actually set up, this is known, u prime of x dx, the integral. This is one property that has elapsed before. We said the integral of u prime is equal to x plus c. So all you put is you put u of x is equal to f prime. If you put u of x equal to f prime, this becomes f double prime. Here, this becomes f double prime, and this becomes f prime, and you end up with this actually expression here. So you use one of the properties of the indefinite integral, and all you do is you put substitution. Obtain f of t if the integral is equal to this, and we know of t. What can we do here? you can use one again the property of the indefinite integral. The derivative of the integral is equal to the function. So directly when you differentiate this with respect to t, you got here f of t, and you got here the derivative of this, and the derivative of this is a simple function because it is equal to the square root 9 minus t squared to the square root of minus 1. When you differentiate this, you use the chain rule, and you end up directly by minus t over 9 minus t squared to the power 3 over 2, and this is your f of t. Suppose I tell you obtain f of x if f double prime, verify this expression here, f double 5 of x equal to x minus 2, while f of 0 is 1, f dash of 0 is 2. This is in fact a differential equation, but it's not a differential equation. Why? Because it's simple. F double prime is equal to the function of x only, and you need not separate. And therefore, this is if you find the antiderivative of f double prime, which is f prime, you integrate x minus 2 to integrate this formula here, and once you obtain f prime, you can obtain f. So in fact, the solution here, first of all, you have to integrate. You use actually this formula here. This is this what we have it as one of the properties of the indefinite integral. The f is equal to the integral f prime dx plus c, or f prime is equal to the integral of f double prime dx plus c. So you integrate f double prime from here, and you get f prime, which is the first derivative of f. If you integrate this, you get half x squared minus 2x plus c. And then this c, how you locate c? You know very well that f prime is equal to 2 when x is equal to 0. So you substitute for x x equal to 0, and because f prime is equal to 2, so c becomes equal to 2, and you end up with this formula here for f prime. Now this tells you that the derivative of a function is equal to half x squared minus 2x plus 2. So what is the function? It's the antiderivative of this expression here. So it becomes directly the integral of this is equal to the integral of this, which is the integral of x squared is half cubic 1 over 3, 1/3 of x cubed. So you get 1 over 6 x cubed minus here the integral of this minus x squared plus 2x plus c again. And this c, how can you obtain? You obtain from the value of f at x equals 0. So it tells you when x is equal to 0, f is equal to 1. So all you have to do is substitute for c is equal to 1, and you end up with this expression for f. Suppose we have an example like this one. They ask you to calculate y in terms of x. Y in terms of x, in other words, y as a function of x. If dy by dx is equal to y, and this is the initial condition when x equals 0, y is equal to 5. In fact, this looks very much like a differential equation in the sense that you have here dy by dx is equal to y, and y naught is equal to 5. So in fact, of course, you can do it by separation. You can isolate dy over y, and you can is equal to dx. You can write this way, but you may not do this. You don't need this. In fact, you can write it this way: dx by dy is equal to 1 over y. And if you write it this way, it looks like x is an antiderivative of 1 over y. And it's not anymore a differential equation. Indeed, it is one, but it is a very simple one. If you know the derivative of x with respect to y, it's equal to 1 over y. What is the value of x in terms of y? What is the function of x in terms of y? So what you do here, instead of it resembles very much this one, dy by dx is equal to 1 over x. Would this be considered as a differential equation? You integrate dy and 1 over x dx? No. All you have to do, since the derivative is equal to 1 over x, the antiderivative, y represent the antiderivative of 1 over x. So in fact, from his, you get directly x is equal to what? To the integral over 1 over y dy. And this gives you what? Ln mod x, but you don't need ln mod x, ln mod y, because y is positive, and you don't forget ever c. So this here tells you what? That x is equal to ln y plus c. This is the solution of your supposedly differential equation, or supposedly function here in terms of x, and you wish to calculate the antiderivative. You wish to integrate this, or you wish to locate to evaluate x in terms of y. So you get an expression of this form. Now you have what? It tells you that y at x equals 0, y is equal to 5. So all you have to do is you substitute x equals 0, and ln y, you got here 5 plus c. And from this you obtain c is equal to minus ln 5. So if c is equal to minus ln 5, what is the value? What is the function x? So you get directly that x is equal to ln y plus c, which is equal to minus ln 5. But the algebra tells you that this is equal to ln y over 5. And if x is equal to ln y over 5, what is y in terms of x? It directly says that y over 5 is equal to e to the power x. In other words, you end up with y is equal to 5e to the power x. And in fact, this is the solution of your equation. And if you differentiate it, you get dy by dx is equal to y. This is how it goes. In fact, with this, we have now exposed our, and this is how it, this is the solution. We can go directly fast with it. This is what they seek, they ask you to obtain. You put dy by dx is equal to y in the converse form. Dx by dy is equal to 1 over I, and then you integrate. And once you integrate, you substitute for c for x equals 0 and y is equal to 5, and you directly obtain your expression here. In other words, y is equal to 5 times e to the power x. In fact, what we said now, if you come to the end of this lecture, if you want to summarize quickly, first of all, we have to say that antiderivatives are indefinite integrals. They are integrals in the sense they can give areas, but areas that are not definite, areas that are arbitrary. And these areas can, in fact, be called antiderivatives of some functions. In other words, whereas the definite integral gives a number, antiderivatives, in fact, are kind of indefinite integrals. In other words, family of curves. If you add up these antiderivatives, you end up with family of curves, which we call indefinite integrals. And if you have two indefinite integrals of the same function, if you have, antiderivatives, two antiderivatives of the same function, then they must differ by constants. Again, what else we said? We said that these antiderivatives, you should always add this function, this constant c. Otherwise, you may end up with the wrong answer. And this constant c would not be forgotten. And for example, to give you an example for this, suppose, for example, they ask you whether capital F of x and g of x here, these two functions can be considered antiderivative of this function. Indeed, it is. Why? Because these two functions here, when you calculate the derivative, you find that you obtain this small function of x. And these two functions, actually, they differ by constant. So it tells you the theorem that if you have two antiderivatives of a function, they might differ by constant. And this is why we don't ask the student, try to find the antiderivative of a function. Instead, we tell him to calculate an antiderivative of a function. And with this, actually, we come to the end of this lecture. And I wish to remind you that you have to know some antiderivatives of some elementary functions, like, for example, the antiderivative of e to the power x, or e to the minus ax, or 10x. Once you know all these antiderivatives, all you have to do, if you are given a problem, you just transform it into some pieces of small pieces of functions, and then you integrate each one alone, and this is why you have to memorize a little bit of some antiderivatives. Before we end up this lecture, I wish to remind you that this lecture, along with the other ones, whether the preceding ones or the one that is going to come later, are all uploaded to the site of the MedNet project, which is administered by the Consortium Nettuno in Italy for long distance learning or online learning. All these courses are uploaded, whether this course or any other course, in a variety of languages, either French, English, or Arabic. They're all uploaded to this site in order to prescribe to this lessons if you wish to pursue your degree in engineering. And until we meet again, with this, we have given an overview of what's the meaning of integration, or the antiderivative especially, and then we move forward to calculate. As I said, this is our next approach. Instead of going directly to the definite integral, we try to explain some very well-known method for calculating antiderivatives, classical methods. And until we meet then, I wish you good luck, and I thank you very much for your attention.